we're done with this discussion session, there will be a league town hall meeting. So stay for that, then go to the posters. You're not saying they should skip the posters just to be with you? No. Anyway. Okay. Now, I'm going to sit over here because otherwise it looks like I am the MC and I don't need to be the MC. So, okay, is this on? Is this on? I'm talking. Do you want me to keep it on? Okay. Now we can share this back and forth. I thought we might start by. I have quite a few questions about this whole area of research, but I thought it's okay we start like I suggested, that we just go down the row here, and the actual title of this session is 4 experts about lunar water plus me. And so we could go down and ask these experts what they think some of the outstanding problems are, and then we can open it up to questions about the whole process. So let's start with, let me introduce everybody. This is Bill Farrell, right there. He works for the government.
I'm here to help you.
Yeah. This is Dana Hurley. She is funded by, but does not work for the government. Carle Pieters.
Taylor.
Oh, yeah, I'm Jeff Taylor, and I'm be your host today. I'm at the University of Hawaii. Can you guess? Yeah. This is Carle Pieters from Brown University, who has been in lunar science as long as I have been, so we know everything. And Tom Orlando.
Who knows nothing.
He's from Georgia Tech. And let's start with Bill, just give a few observations.
Okay, well, in the last 10 years, there's been a lot going on. Oh, it's not on? Hello, can you hear now?
No, I think it has to be up.
Oh, it has to be up. There you go. That's the problem. All right, so already we're making progress. Well, I'm actually a plasma physicist, and I used to study the lunar wake, the trailing void behind the moon when the solar wind would flow. And we always said, well, gosh, the solar wind just is absorbed on the front side of the moon, and you get this trailing wake, and it's actually pretty spectacular. It can go 30 lunar radii behind the moon, the solar wind lunar wake. And we always just say, well, the solar wind's just absorbed on the front side. We didn't really care too much about what was happening there. But in fact, there's a lot going on when that solar wind hits the surface. And I think in the last 10 years, we're learning a lot more about that. The surface, the oxide-rich surface is really a little conversion surface. And the solar wind protons that come in can actually, they just don't get, quote, absorbed. They actually, some go in and stick, but actually the surface can re-emit those same protons as H2, can re-emit them as neutral hydrogen, can actually reflect some of those protons right back out as reflected, as reflected protons. And then those hydrogens that stay in the surface, some of them diffuse around and leave, and as Tom's talked today, he talked about this, some of them stay and hang around and maybe stay around as long-lasting hydroxyl. And all of this is coming together really in the last 10 years with spacecraft like Kaguya, Chandrayaan-1, LADEE, LRO, of course, and LAMP. So it's really kind of a revolutionary time, the way we're looking at hydrogen. And actually, almost like a topic are the words hydrogenation versus hydroxylation versus hydration. Where does the H's end and the OH's begin and the H2O's sort of form? And probably Tom and I, we could probably talk for, all of us here could talk for a long time on those boundaries. And maybe they're not as distinct, but it's amorphous and diffuse, those boundaries between those different processes. Anyway, I think I'm done.
All right. So one of the topics that I'm really interested in and think is a big puzzle is trying to understand the polar cold traps of the moon and the distribution of water there and how that can tell us about the sources and the loss processes. One thing that's becoming clear as we've gotten a lot of data is that it's a very heterogeneous distribution. And so, that implies that you have either some very localized processes that are acting, but we haven't found a explicit tie to temperature and the distribution. Although it's related, it's not a one-to-one correlation. So, or you have some old, maybe that means that the polar volatile deposits are old and they've been broken down and made heterogeneous over time by impact gardening and other processes that might affect those. But then if you have something like that going on, that implies it's a very old deposit. What about all these volatiles that are on the moon now on the day side that we see a diurnal signature? How come they aren't contributing? So it's a puzzle. There's the distribution and the cold traps that has implications that maybe we're looking at very old things, but we also are observing ongoing processes going on that should deliver a very smooth distribution of volatiles to the permanently shadowed regions of the moon. So why don't we see them as being more homogeneous?
Carle.
Okay. Well, 10 years ago, I never thought I'd be up here talking about lunar water. And boy, has a lot happened in 10 years, a lot. At that time, we thought, well, maybe there is these permanent shadowed areas that are predicted to accumulate water, and everybody was busy working on that, and that sort of was ingrained in people's thinking. And then we started finding water in lunar samples. We found water all across the surface, but we did not find a lot of water at the poles, so it got very confusing. And we're still confused, but only in the good sense, in that there's so much to do, so many questions that we have. I've got a question I'm going to ask halfway through this when we get a chance that I'd like to ask all of you, but right now I'd like to sit back and listen.
So I was stimulated by a lot of the advances that Carle just described, and I wasn't active in the issue of water on the moon until these were coming out. And Carl Hibbets alerted me to some of this, and he sent me a spectra, and I said, yeah, we have that spectra, and it's OH, and it's what you expect from minerals, right? And then we went on, and there's discussion of, well, no, there's water, there's molecular water on the moon. And I said, well, I don't know if it's molecular water on the moon. What is the sticking probability and the binding energy of water on lunar material? Because that should be, that'll answer that to me as a surface scientist. So I come at it from a very different perspective. And so we said, okay, well, let's do this. Let's just measure the binding energies of water on the moon. And we started out with JSC1A. And then I met Larry Taylor, and he said, what are you using this junk for, right? You do the real stuff, right? I said, I can't get the real stuff. He goes, well, come on and visit me, and I'll give you the real stuff, right? So anyway, we did get some real stuff. And then we started to measure the binding energies. And then I started to talk to Bill. And he said, oh, I'm glad you're doing the real stuff. Now, I like these binding energies. And then we went through some of the models that he was developing. And I know we're going to go real full circle, because I think Bill is right. There's a lot of confusion as to what's going on. And the solar wind is really important with regard to the energy deposition and turning on chemistry. But it's not a one-shot deal. And so there's a lot of sort of, processes that are turned on during that impact. And then, stuff is at low temperature. And so there's not a lot of chemistry that's happening at these low temperatures. And so there's a convolution of this. And then I began to read a lot more about what's going on in the survey program. And then I'm learning a lot more about meteorite impacts. And Dana's doing these transport models. And I'm like, this has to be part of this. These micrometeorites have to be part of this. How are they not? This is a really good way of delivering energy that's not delivered by proton impact. And if I've got everything dressed up, if you will, by the protons to react and form water, but I need to get kicked over to the barrier for it to happen, the meteorite is the best way to go, right? So a lot of people were surprised for me, when they heard me talking about this and saying, you're not giving the electron credit for anything, right? Well, this time, I think it's not the electrons, it's the protons and then these impact events. But there's a lot of, none of this can get unraveled without everybody working together, where we have the plasma modeling, the transport modeling, the geochemist, and Carle, Hibbets, and Darby always telling me, you're looking at the wrong stuff. You got to look at this stuff. Or look at what the real geological parameters are. And because one thing we're finding, and nobody called me on this, and I thought somebody was, when I said, okay, the recombination temperature is at 450, that's true for a nice, perfect silicate. Right? But none of these are nice, perfect silicates. And so one thing we are finding, and Andy Rifkin will like us to write this paper up because we keep telling him we're going to write this as part of his vortices program, is when we really look carefully at recombinative desorption off of lunar materials, that shifts down a little bit. That temperature and the recombinative desorption temperature actually shifts. It's not too low yet, but I think there may be, so the composition of the material changes the story a lot, right? And so it would be really good to get a good handle on what compositions matter the most.
Anyone have any comments about that before I open it up more for other people to comment?
Hurley does.
I do, actually, because that was one of the things I wanted to talk up, and I think it's related to what you're talking about. I'm thinking about different parts of the solar system. We've got the Mercury situation and the polar deposits of Mercury, which we probably ought to go back to. We have a few deposits on Ceres in the permanently shattered areas. But with the hydration that we see across the surface of the moon, it's silicate, it's hydrogen, it's all these interactions that are occurring on the surface. We don't see that at Vesta. Vesta is a wonderful basaltic surface. It has solar wind. It's nominally anhydrous. We do see water on Vesta, but it's clearly contamination. It's clearly been brought in. We don't see it with any of these temperature or latitudinal relationships. So there's something, and perhaps it's associated with the specific chemistry. Does it have to be very plagioclase rich? Or does it have to be very battered? I don't know does it have to have these dangling bonds that Darby likes? What is it about it that makes the character of what we see at the moon distinct from what we see elsewhere in the solar system? And that's some of the questions I'd like to raise.
Let me point out, though, that the surface seems to be different, but if you look at eucrites and look at apatite in them, there is water in them at small amounts, but it's not that much different than Inamari basalt.
But that's the second form of water. That's the internal water, not the external.
Quite right. So the surface environment affects all these processes on the surface, which is what you were saying.
Mm-hmm. I mean, so one sample that Darby did give us that we looked at before we went to the real stuff, and she would say this is the real stuff, was a glass, right? And it was to simulate the rim. Okay. And she had a well-defined composition. But there were no dangling bonds. Okay, so what stuck? Ice. Okay, you can't get chemisorb water on the glass.
Okay, so you didn't see any OH, you only saw...
No,
okay.
Well, there's OH, but then there's not strongly bound water. Okay? There's nothing that's not anything more than water on itself. So the strongest interaction was water with itself, right? Now, if you broke the glass and you ground it up, then you can get it to stick. And so you have these unpassivated bonds, and then you can get it to stick. So the more ground up it is, and the more, immature the soil is, the more reactive and the higher the ability it has to keep the superficial water.
Which is what happens on the surface of the moon and Mercury.
Oh, yeah.
And yet Vesta too, probably, you would think, and yet you don't see it.
Yeah, we see a different. We do see contaminated water on Vesta.
I did want to get back to something that
Or
Dana
OH.
mentioned. Is that, this is on, right? Did want to get back on to something, Dana, you mentioned, which came up earlier, which is in the polar regions, the difference between the superficial frost and the more buried water that don't seem to match up. And so, you know, are they different processes? And, you know, what do people think is going on? And can you use the surface water as measured by LAMP as an indicator of the larger resource, really? You know?
Yeah, well, from a resource perspective, I think it's the volume measurements that are the most important, because you're not going to just glean what's on the surface. You really want to understand what the content is over a large volume. So the neutron data, and, you know, if there were any sort of deposits found by radar, that would be really useful from the resource perspective.
Hey guys, can I interrupt for a second? So I just wanted to remind you that although we've been sitting in on the volatile sessions pretty much all day long, there's been another whole group that's been in the other room. And I feel like you've jumped in at such a deep level that there could very well be people in the room that are just getting nothing out of this. So, so could we step back a little bit, and maybe, Dana, could you maybe give an overview of what we did at the internal workshop? That might help put people, or whoever wants to, but, you know, give them a foundation. And then I've got the mic, and the whole point of this is to get the community's involvement into this topic as well. And so when you guys have questions, just raise your hand, and I'm going to bring this to you so you can be part of this, okay? Great.
Okay, so at the internal workshop that we did in November, we had discussion sessions for 2.5 days, 3 days, something like that, based on several questions. And we broke it out into 3 different categories. One was internal volatiles, one was polar volatiles, and one was global volatiles. So the internal volatiles, that's the volatiles that are stuck in the rocks that are, you know, we're finding in the samples now that were left over from the formation of the moon. The polar volatiles are the volatiles that are in the permanently shadowed regions at the lunar poles where it's really cold, and so it's one of the few places where some of these constituents can be on the surface or near the surface and be stable, like water or CO2 or mercury, some of those things. And then there are the global volatiles. So that is the water that M-Cubed and LAMP have detected on the surface of the moon, even in daylight. Could be OH, could be H2O. That's something that is under debate. And it's a very thin layer as far as we know, because from the observations that we have that only detect the surface. And that global water or OH seems to have a latitudinal and a local time distribution. And one of the big questions that we're still trying to understand is whether that means that you actually have water or OH that's moving around on the moon, or if you just have some observational biases that are making it look like it's changing, or if it's being constantly produced and lost in place. So is that?
Thank you.
Okay.
Yeah.
Yeah, so I was, in fact, about this to open up to everyone, although I admit I was only thinking about people who went to the volatile sessions. My apologies to the rest of you. Too bad your interests are not in line with ours. Hey, all right, so does anyone have any questions here just to ask the actual experts?
Okay, here's one. Please use the microphone and remember to identify yourself so that everybody else in here knows who you are.
Rich Miller from University of Alabama, Huntsville. So one of the mysteries since the late 90s, since Lunar Prospector flew, was the shape of the polar hydrogen deposits. And as you probably know, last year we published a paper with Matt Sigler and James Keane and others, which showed through a series of circumstantial arguments that a non-trivial fraction of that hydrogen at the poles may be quite ancient, and evidence like antipodal nature at the north and connection between north and south at very high significance level, looking at the temperature distributions at an earlier orientation, the development of the PKT. And so that explains the spatial distribution of the bulk polar hydrogen quite well, but it raises another question that's outside of my wheelhouse, and this is what I want to ask you. About half of that polar hydrogen, if this argument is true, is quite ancient, billion years or older. Can hydrogen be stable, water be stable that long in those polar regions? My understanding is that's quite a bit longer than many of us thought it could be stable.
That's a good question. You want to, Tom?
So, that's one of the things I tried to tell you this morning, is that when the proton comes in and it makes a hydroxyl group, that's part of the mineral, and that's not going away. That's really, really stable. Now, it does go away if you get above 450 degrees Kelvin, but the polar points aren't getting that hot, right? And so that'll stay. Hydrogen, H2 and H, they're going to recombine and they'll diffuse and they'll leave, and that'll be the first to leave. If you're able to get some recombination, make water, and water has a self-diffusion rate, it's pretty slow at the polar temperatures. That'll stick around a while, but if I'm able to incorporate it and trap it, or as, make it as a part of the mineral, then that's going to be around. And that'll count as hydrogen from a neutron measurement. That's going to count, right? But that's really part of the mineral from my perspective.
Okay, and at the workshop, I remember you and Bill had just a bit of a differing opinion about the OH staying. Like, you could form it, and then would it stay long enough to be able to hop, or long enough to make for another H to come in and make water? Could you two talk about that a little bit? Because that was really interesting.
Well, this is more, rather than, it's not the polar H so much.
Right,
but
right.
it was-
This
it
is
was
at
the
other
mid-latitude,
latitudes. But the idea of
hydrogen.
maybe some of that water eventually getting into the poles was an interesting idea. But what I took away was it probably doesn't happen that way, that stuff probably doesn't hop up there.
So that's my opinion, is that for the OH, it's not, unless you heat it, or you have an impact event, or you have some non-thermal process that gets you for it to happen. Once it happens, and then it leaves, and then it's, leaves the surface. If it doesn't have a genes escape, it'll come back, and then this is Dana's problem. It's got to, and she can model the transport of it, right? And then it'll hop around and stick in the cold part, right? So where Bill and I were talking is the, stuff is moving around in there, right? And so the question is, what is moving? And the hydrogen can get dressed by an oxygen vacancy and not actually make an OH, and the hydrogen can move around.
Right.
Right? And, and that happens, right? And then, and it could slow it down, and so the transport of the molecular hydrogen is not going to be as good as or as fast as you think it might be.
Right. So in Tom's talk this morning, he talked about the fast hydrogen, and then the OH, the part that was sticking a little longer. But the fast hydrogen is sort of quasi-OH, and that's where we're sort of, is it hydrogenation or hydroxylation, or maybe it's a blend, where
Yeah.
those hydrogens are just lightly bonded to the O's and they're jumping from O to O, but delayed.
But the O isn't moving. The
But
O
the O is
isn't,
not moving,
and
right.
on average, there's a hydrogen there. And if it's moving, and he wants it to move, it can move, but the optical measurement is looking at the ones that don't move.
Well, maybe.
Okay.
Questions? Okay. Pam?
They don't move away. They have an amplitude motion, but they're not lost.
I just can't help but say this. So now, at this point, we have essentially we'll have proven core technologies to do basically multi-platform missions, either on the surface or in orbit, or both. There are still some thorny issues, but we're in the process of dealing with most of them. So what I'd like to hear from you guys is talk about if you could design something, a set of these orbiters, let's say, or this is on the surface, little landers. We have a lot of landers that are supposed to be going to the surface in the next 5 years from a variety of commercial folks, Astrobotic, MoonX, and several others. And they'll put things in orbit as well, at least on their second attempt, or maybe they'll do that on the first attempt. I don't remember. But what would you like to bring along as a payload? Let's say you could do 3 relatively compact instruments, combine UV spectrometer, some kind of a particle analyzer, some kind of an imaging device. I'd like to hear you talk about that a little bit, because I think it's pretty exciting what we could potentially provide in the way of taking simultaneous measurements from these different venues.
Talking about landed on the surface measurements?
Yeah, either one. I mean, I'm trying to, as I've been trying for 5 years, to look at developing essentially a packaging technology that would allow you to fly maybe 3 sensors that could take data during lunar night without having to spend money on the radioisotopes.
Yeah.
That could essentially be deployed from a lander deck and operate on a standalone basis, or in orbit either. I mean, or combining the two.
Who wants to field that?
Has
Let
anyone
me-
here been PI on an instrument that flew around the moon? Oh.
Yeah, but it was very short-lived. Before I even get into that, that's a good question, Pam. But before I get into that, I think it's important that we come back to Dana's introduction and remind ourselves that we're talking about 3 different forms or types of water, each of which has a different origin and each of which has different processes that are associated with it. So one size does not fit all for those. And just to refresh those of you who haven't been involved in the water discussion, there are the polar deposits, which we believe have been accumulated and sequestered in the shadowed cold areas, and that's one form of water. There's the surficial water, which M-Cube looked at, which is a lot of the OH linked, but it could be very much surficial that may get gardened in. And then there's the endogenic water that started with the formation of the moon and was sequestered in the mantle and is included in the basalts and the primary lithologies that we have in the samples. And samples are required to study those. So these are 3 different forms, and they address different processes that are fundamental to lunar understanding the moon and the moon's history. So we can't answer that with one answer, Pam, because each one requires its own set of answers. Yeah. So who wants to pick which type first?
Oh, I got something.
Go ahead.
So, I think a important science problem to address is to constrain the sources and the sinks of, what volatiles are coming into the lunar system today. And so, some sort of instrumentation that's going to follow the solar wind. So you have to have your monitor of the solar wind influx, and then to be able to follow how that solar wind comes back out, because it's not accumulating on the moon over time. There's some steady state where as much that's coming in is going out. And so is it leaving as H2? Is it leaving as energetic hydrogen atoms? Is it being converted into water? It may live on the surface for some lifetime as OH, but eventually it's got to get replaced because there are protons hitting the moon constantly. So having some ion mass spectrometer or neutral mass spectrometer that can witness those loss processes to see exactly how that solar wind is coming back off of the moon is a really interesting study, I think.
would you have one of those in more than one place? I mean, is it better to have a network of, so you could follow the path to the poles, or?
Yeah,
Yeah.
I mean, I think you can accomplish a lot of that in a polar orbit because then you can see everywhere at some point in time. The important thing is to have enough measurements that you can disentangle all the different drivers that are causing variability. So, you know, if it's a very short mission, then having multiple instruments will help you constrain the spatial distribution at the same time. But if you have a longer mission, then you can try to detangle that just by more observations.
But if you had simultaneous measurements, then you could constrain a lot of things that you can't with just one platform. So if the sun is doing something anomalous, for example, you're going to see that whenever you're over the illuminated hemisphere, being able to separate that out as an effect. It's the nice thing about having simultaneous.
Okay. Jerry Sanders, Johnson Space Center. I have a question for the polar volatile part of the discussion. I haven't really heard anything so far talking about how porous or how fluffy the surface regolith may be in some of these permanently shadowed craters. And I just wanted your thoughts on, depending on the porosity and fluffiness of the regolith, how do you think that would affect the deposition and the retention, or the, you know, the movement of the hydrogen and the OH or water in those shadowed craters?
So I'll
You go
take a
ahead.
quick step.
Yeah.
Okay. I mean, you know, you think of these surfaces, if they're exposed, like activated silica, you would think that it would be a really strong adsorbing source, adsorbent surface. So it actually makes stuff stick better to then start to get a layer of condensate. But you know, like in cryo pumps, usually start with adsorbent, and then you get condensate on top. And you know, fluffy regolith that's maybe got a little touch of solar wind coming in. I mean, that's going to be a really activated, you know, it's probably industry grade adsorbent in terms of starting things. So you're going to get adsorption first. And the question I'm wondering is whether on the moon, now on Mercury you do get the condensate and the block ice. On the moon, does it just stay a absorbing surface and you never really get the ice? Well, you're really seeing it 2 or 3%, you know, of water is really, you know, absorbent process and not a sublimation condensation process like the, you know, Watson and all 61 thing. Maybe different. Maybe
Well-
more like what Tom does.
Well, before you answer, there's one question that is sort of embedded in your question that we haven't addressed, and I'm not sure we're ready to address, or we need other people to address, and that is the link between what we see on the surface, whether they're in the permanently shadowed areas, and what the neutron spectrometer is seeing, which clearly is at a greater depth. And we haven't made that link yet. You know, and that's a key one, certainly for the moon. And what I'd like to hear is what do we need to do to make that link? How do we resolve? We have both of these clearly happening at the poles, but how do we link the data that we do have? How does that make a self-consistent story? Is it gardening? And the polar wandering issue, you know, these are clues that we've just learned. How do we put it together?
Well,
Somebody out here has the cue, so you're
Okay.
finished with this question.
so the porosity is a big deal. I mean, so the higher surface area that Bill mentioned does help out a lot with regard to sticking and sort of contact area. But if it's cold enough, it's going to hit and stick. And so, and the question is, how much does this water bounce around? Ultimately, you're going to be able to stick on all of these grains, but then the issue comes with regard to transport, and if I want to move stuff around. And very often the diffusion is grain-to-grain diffusion, and whether or not you're touching, and then you want to minimize your void fraction. And then this also then affects thermal transport and the thermal properties, and so, you know, a lot of the properties, and then the mechanical properties and how much they stick. Right?
Enhanced by being highly porous?
Okay, so, you know, I have invited a mechanical engineer on our program to help us model diffusion because I don't know the answer to that. I really don't.
I have two questions. Madhu Thangavelu from USC, University of Southern California. One deals with engineering and the other with geology. The first one is about engineering. The resource prospector, why is it so small? And can you imagine a larger prospector that is built on something along the lines of the Mars Science Lander? And the second question is about the lunar lava tubes. We know a lot of them exist. Is it possible that there is some mechanism, some physical mechanism that allows them to have water in it, water ice or any kind of volatiles?
Let me just first turn the spacecraft question to Jerry.
Right, yeah.
Because they have thought about this and thought about what
Yeah, the size of RP is driven by competing aspects of how many instruments can you include, including a drill that goes down to at least a meter plus other things, which would tend to cause the rover to get larger, to the competing aspect of cost and trying to get it to the lunar surface. So from day one, we were trying to be in a 200 to 300 class rover mission from both trying to keep the cost down, but try to have enough instruments on board, such as a neutron spectrometer, a near infrared spectrometer, with a drill and volatile analysis. So yes, you can have a larger rover. And if we actually find something in RP that looks interesting, because again, as others have mentioned, it's solar powered, so it's very short duration. Should we find something enticing, then the obvious question would be, can I have a nuclear powered rover or something that lasts longer? And so I mean, really, you got to look at whether it's RP or orbiters or whatever as stepping stones and hopefully a larger, more international plan.
Anyone want to talk about the lava tube question? Because I can add something from my vast base of ignorance. The lava tubes, first, an interesting thing about them on the moon is that they generally are where the lava flows are, of course, and that is generally where the near side Maria, which are in the Procalarum creep terrain, which is where the concentration of heat sources are and radioactive elements, so that the lunar gradient, the temperature gradient with depth is higher there than it would be in the poles, and the result is probably the lava tubes don't get cold enough to have ice deposit or things to stick well enough. That's my guess, and I'm sure it may have been modeled, but it sounds like a relatively easy kind of modeling job because you can calculate what the heat flux should be, and the poles don't have that, but they don't have lava tubes either. So it's kind of a so my guess is, although on the other hand, to me, it's there are these permanent ice features in lava flows on Mauna Loa. There's some in New Mexico, and that's because of rain getting into them, freezing, and the cold temperature keeps up with the warm temperature, so they're permanent. But I don't know if the flux of the cold is good enough, and there's no air temperature to change, so that it's kind of the heat flux from the moon. So,
Yeah, don't we need the thermal heat flow measurements a few more?
Speak up.
we could. Carle is saying, no, we need more heat flow measurements, and it would really help for a number of things to understand lunar thermal history. The one we had for the Highlands, the Southern Highlands, was not deployed, so we don't have those data. The other places on the near side are in the Procalarum creep terrain and in an odd location near the edges of big basins. We could use that, which would help pin down not only just what's the temperature gradients inside the moon, and including at the local places where we would install them. South Pole, by the way, is a great place for one, too. But it sees the integrated heat flux from the radioactive sources, so you get an idea of how much, better idea of the distribution of uranium, thorium, and potassium, especially uranium, thorium, inside the moon. So it'd be very good. But I don't know if we can justify a mission to do that.
Of course we can.
So I have a question. I think based on what Carle was saying earlier, it would be wonderful for this audience if you guys would say what you think the questions are that we really need to be working on or addressing, or what is needed to make progress on any of the big questions that were left unanswered. So it just itemize them, make them clear. Is there a way to do that? Is that a hard thing to do, or could you, do you have some things on the top of your head that you could say?
Can I toss one out? And actually, this gets back to, well, let me preface it. We do have lunar resource prospector that's planned. We have several other of the international teams are planning landers. Almost all of them, and correct me if I'm misstating this, almost all of them are geared towards polar areas to look for buried water. And that's a principal goal, because it's hard, and we need information on that. I'm interested in the water cycle, and you need different kinds of instruments for that, not just drilling. You need long-term, you need instruments that can measure over a lunar day or 2 or 3. And so these are the kinds of instruments that we haven't had, certainly since, well, we haven't had for quite a while. And I would really like to hear people thinking about those kinds of instrument packages that we can be addressing the water cycle issue, which does require multiple measurements over time, different illuminations, because it's clear that is a key for a couple of these kinds of water issues that we're addressing. And we haven't had much discussion within the community on that.
And is it strictly observational that you need, or is it also theoretical modeling or some?
Well, clearly you need both, but we don't have the data yet.
Okay. Raise your hand if you're interested in saying something, and I'll come to you.
Along those lines, one of the things about measurements that hasn't been discussed a lot is about where you take the measurements. So one of the reasons why RP is a very short duration mission is it's solar powered, but it wants to go to a place that is predominantly shadowed with very brief periods of sunlight. So talking about your measurements over longer periods of time, and some of these other international missions are going to places that have much longer sunlight, but then how relevant is the data to what we're trying to do. So there's this balancing act of where you place your instruments and what power sources you may want to use. So I'd like your thoughts on that.
Okay.
Long lived.
With
Okay,
mobility.
now I have a dilemma. We have 3 minutes. I have Rosemary, I have Clive, and I have Tim. So I think we may be at our point of questions before we have to end. But can I go with you next? And then Rosemary, I'll get to you in a second. Okay. Since I'm up.
Okay, I'll make it quick then. So next discovery round may be coming up sooner than we think. Last time we had 2 lunar proposals. That was it. What can you do with Discovery to address some of the issues that you've been discussing?
Yeah.
I'll make it longer.
No, you stay short.
Carly's got a long list.
Yeah, you stay short, but I'm going over there, and we've got to.
Oh, no, it's for them.
Yeah, no, anybody who wants to answer his, but I'm going over there.
Well, I mean, so you can do a lot from an orbiter still. And there was the League VSAT that Paul Lucy led that has a report of the measurements that remain. From an orbiter, you can try to understand the water cycle that's ongoing now. As Carle was talking about, I mean, you can make a complement of instruments that will look at sources and losses and look at the surface to see what's adsorbed on the surface and try to really get some good data, the data that we're, just shy of with the current instrumentation. You can also do landed missions for discovery on the moon that, can look at what is actually happening on the surface. You can imagine, for example, a mission that, lands in a magnetic anomaly and drives out and tries to understand the difference in the regolith when you have the solar wind interacting with it and when you don't. Because, that will help understand a lot about, what role the solar wind is playing in creating any sort of hydroxylation or hydration.
There's about 3 missions right there.
Yeah.
Right, right.
Yeah.
So we need some teams to put them together now.
Right. Well, still one of the biggest questions is probably how this modern water cycle that we're talking about, the impactors, connects to the reservoirs. And the question I'm wondering, particularly after Matt Siegler's work, is the reservoir really disconnected from the modern water cycle? And the reason why that's important is if we're going to use that reservoir as a resource, is it a renewable resource or not? And if it's not renewable, then is it just a water park, an international water park that we never use? Like, or if it is renewable, it's like a Georgia pine. We can actually, make use of it, and it's going to build back in. Might be 100 million years, but we just haven't, we won't deplete it.
Oh, Bill, you've touched on one of my favorite topics.
Okay.
But frustrations too is that this whole concept of renewable water on the moon. Wow.
Right.
But we don't have the data for it, and getting the key pieces of information that can measure the water cycle, measure the time scale on it works, and measure the amount so that we know to what extent it is renewable. Because if it is renewable, wow, that's a huge opportunity right there. Wow. But that's a big if. We don't know.
Right.
Rosemary.
Oh, okay. Rosemary Killen, Goddard Space Flight Center. And I have a fundamental question for Tom Orlando in that what is water? If you have dangling oxygen sitting up there and hydrogen comes in and it starts vibrating like it is water, is it really water? If the oxygens are stationary and the water is hopping, is that water, even though it might have a water signature?
So the water has to have 2 OH bonds, okay, period. And for it to be an isolated, and then the water will bind with itself, and water will bind with the mineral, right? But unless it has 2 OH bonds, it's not formally water. And so you need 2 hydrogens, right? And you can have OHs and hydrogens hopping around, but if it doesn't form another OH bond, and then remove it from so that it can be removed from the mineral, that's not formally a water molecule from a chemist's perspective.
Okay. So going back to your point, Carle, and recognizing the desire for a longer-term mission to make kind of sustained measurements that might require, say, a nuclear power source. Do we have any understanding from either a scientific or an engineering point of view how warm a spacecraft can be on the surface before it starts to alter the environment and change the measurement? If you have a source that's putting out heat, is that going to change the environment to the point where our measurements are not meaningful anymore?
That's a good question. I don't have an answer, but we do know that the surface varies enormously. It goes up to 400 K and down to what, 150. So the thermal cycle on the surface, and actually you know these numbers better than I do. Oh, well, yeah. Oh, yeah. If you put anything in there, will it melt? Yeah.
Yeah. The more general question is, it's clear we have a lot to learn, that more measurements are needed.
Yeah, that's
But
it.
how will these measurements affect what we're measuring overall? How will our presence of more spacecraft affect what we're measuring before we understand it? When should we send humans back, especially to live permanently, before we understand the fate of the water that they will leak out? And by leak, I mean leak. And so there's a lot of questions that really does have to do kind of with planetary protection. At what point do you start big prospecting operations, let alone mining polar water? Do we want to understand everything first, or at what point do we stop it and say we know enough and now let's use the resource? Those questions are very important, and so we should keep them in mind too.
Eric, did I not understand that if you have a hydroxylated mineral and you roast it, you can get H2O off it?
Yeah, that's for sure. You don't have to roast it. I mean, you just have to, it could be a s'more. It's a little bit toasted.
A rotisserie chicken.
No, it's the temperature is about 400. The lowest temperature we've measured for gibbsite is like 350 Kelvin, but most of the stuff is around 400 Kelvin, 450. And then and so what happens is you got these OH groups that are pretty much next to one another, and they start flopping around, and they have enough action to form a water. So then in that case, one hydrogen does move over. It's related to Rosemary's question. So that hydrogen moves over, and you form two OH bonds. Well, okay, now that's a water molecule, and that leaves. And then the remaining oxygen just makes another bridge between the two silicon, and then that heals the mineral. And then the water's gone.
This was just a quick question about the temperature impact of rovers in permanently shadowed craters. I was just going to refer the person to Astrobotics, I think around 2009 or 10 timeframe, did a number of papers on the thermal modeling of their rover in a permanently shadowed crater and the impact of radiation, seeing the surface and such. So look into that if you're interested.
You want to say something? Let's wait till this question.
Yeah, go ahead. Do your question.
No, go ahead.
Okay.
No, go
Cody
ahead.
Schultz from UCF. What do you see as the path forward, either from a policy perspective or technology, before we can start utilizing resources on the moon for supporting maybe human missions or robotic missions?
Policy?
The government.
I don't think we're the right panel.
No, I would say that you can. I think the key question is not that we can't now. You could land. You could take Resource Prospector and land it there and almost start to use the resource, certainly to characterize it, but you could understand how much there is. The real question is, when should you? When do we understand all the processes before it is impossible to then understand those processes because we have so changed the environmental conditions at the poles? And so, I think that's the key thing. Not that we can't. We could do it right away. There's a lot of things we could do right away if with coherent planning and appropriate support. So,
in a previous life, I was part of planetary protection, and back in one of the bushes, when we were going to go to the moon and do all these things, and send everything, a mission every other year or whatever, and there's going to be a lot of activity. At that point, it was raised, well, maybe we're going to mess up the moon. Maybe we're going to just take stuff up there and really mess it up, and we can't do our science anymore. And the COSPAR Planetary Protection ended up making a recommendation specifically for the moon. And I don't know if Margaret Race is still here. She can correct my terminology. But the moon is not just, you can't just take everything to the moon and leave it there. whatever you take to the moon, you have to now at least document what you're taking. So if you're going to have a spacecraft hit the poles, you have to at least say what you're taking, and that at least is part of the documentation that needs to be done now for the moon for that very reason. Of maybe this is a place we need to protect in terms of the environmental. Now, how far that's gone, most people don't even know that that regulation is there now, or that part of planetary protection is there, but it is, and I think it's a good thing.
Well, I think that's a wonderful reminder, and since we have Alan Stern with us right now, I mean, he just got here this afternoon, he's way down here, he's very jet lagged. I'd just like to remind everybody that what I remember is when Laddie was conceived, I heard him first talk about protecting or finding out what we know about the atmosphere of the moon first before we kept sending more things down. And I thank him for that. I think that was a wise attitude then and is now. So
The other thing this gets into is experiments that are active. You can imagine purposeful gas releases that are tagged to see what happens, at least in the local area. Those could be very informative, but they're big contaminants. So all these things have to be given appropriate thought and planning. Okay.
Okay, I have one more thought, and that is, in order to understand the water on the moon, we need to ask the question, why are the craters, the polar craters at Mercury, full of water ice, and the polar craters on the moon that ought to be cold enough to retain water aren't full of water? That's
Well,
in my mind, that's a big question. It's
So
why?
I'll give you a provocative, maybe, or maybe a completely dumb reason, right? But this recombinant desorption that I say happens, it doesn't happen on the moon because it doesn't get that warm. I was talking to Matt Siegler about this, but it's always that warm on Mercury. And so there, but there, not in the poles, but so there's regions where you can't build up enough OH where you can have this recombination reaction, but there's bands on Mercury where you can actually get it so that it's kinetically competitive to build up enough OH, then to have them recombine and then form water. And those bands are actually close to the poles. They'll then desorb and then they'll hop. And then they'll get to a cold point in a cold region, then they'll stick.
Oh, so you're saying Mercury can make water?
Yeah,
whereas
for
the
sure.
moon can't.
Yeah, Mercury can make water because the temperature is high enough for
Okay.
this. Then this assumes that the geochemistry is similar and that they're similar materials, right?
Oh.
But then that thermal process is like full scale on Mercury. Okay?
Right, the recombinant
And then there's regions where it won't work because the kinetics are wrong for the buildup versus the loss. But then there's bands on Mercury where the kinetics are right, and they're actually near the top and bottom of Mercury. And then
I've always liked this explanation because you know what? You can't get blood from a turnip, but what you're telling me is you can get water from a rock.
yes, I
You
am.
know?
You can.
And
You could squeeze it, but you don't have to squeeze it very
If you-
hard, right?
I mean, it's kind of a cosmic, blows my mind,
that was great.
Okay.
Jeff, I'll let you wrap it up, but I think these guys need to be
Yeah.
finished here so they can come right back in 5 minutes.
Yeah, that's right. So now, the next things to happen, thank you everyone for interesting questions. And remember, first, is it free?
No, it's not free, I'm sorry.
Is it, but not overpriced?
It's not overpriced.
Okay.
It's exactly what we had to pay for it.
There's adult beverages at cost. And get it, but then come right back in here because there's a league meeting that can't last too long because we have a poster session tonight. And we don't want to miss any of that. So thank you again very much for being attentive and coming.
Yes, and let's thank our